Hello everyone, welcome back to our channel. In the last lecture we had a discussion on general introduction of mass spectrometry, basic principle, applications and its limitations. Okay, let's see the next concept, that is what? Molecular ion, its origin, stability, recognition and utility. These are the four concepts which we are going to discuss in this particular video. Okay, we all know that the generation of molecular ion. How can we generate? In the first component, origin, if we see, the molecular ion is generated from the sample molecule. The sample molecule must be in the vapor state. If you supply the electron beam of energy in between 7 to 15 electron volts, approximately 12 volts of energy, approximately 12 electron volts of energy is necessary to generate a molecular ion. This is what? Molecular ion. We have removed an electron from the molecule. Already we know that organic molecules containing even number of electrons. The organic molecules containing what? Even number of electrons. From the even number of electrons we have removed one electron. That's why the molecular ion is going to be odd electron ion. Okay. So let us see how can we generate the molecular ion in organic molecules. We all know that we have three types of electrons in organic molecules. What are those? Sigma electrons, pi electrons and n electrons. If you remove any one of the electron from the molecule, we can generate the particular molecular ion. Right? If you observe the ease of removal of electron, we all know that n electrons are loosely held by the nucleus. That's why we can easily remove the n electrons first, followed by pi electrons and sigma electrons. Let's see the first one, that is what? Sigma electrons, the molecules containing only sigma electrons. The sigma electrons may be only containing CH bonds. Okay, that is what? Alkanes. Take the simple alkane, that is methane. Here what happens? In case of the molecules containing only CH bonds, what should we do? We need to remove one electron from any one of the CH bond. One bond means two electrons are not. That's why remove one electron from this bond, thereby we can get plus radical. In this way we can generate molecular ion. If the molecule containing only CH bond. If the molecule containing both carbon-carbon single bond and carbon-hydrogen single bond, what should we do? We need to remove the electron from carbon-carbon single bond. See the example? Here we have CH bond and CC bond. So according to rule, what should we do? We need to remove the electron from carbon-carbon bond. Thereby you will come up with this kind of molecular ion. If the molecule containing a straight chain carbon skeleton, see this one, this is one example, butane. If the molecule containing the straight chain carbon skeleton, what should we do? Always we need to remove the electron from the terminal carbon-carbon bond. See this one, with respect to this particular moiety, this is the terminal carbon or not? So from the terminal carbon what happens? One electron is removed. In this way we can generate molecular ion. In case of branched carbon skeleton, if the molecule containing the branches, then what should we do? We need to remove the electron from the higher branch. See this one, this is the molecule. This carbon is containing high substitution or not. That's why what happened? We can remove the electron from any branch. In case of the cycloalkanes, what should we do? We need to cleave any one of the carbon-carbon sigma bond. Thereby we can generate the molecular ion. In case of alkyl cycloalkanes, what should we do? We need to cleave the substituted carbon-carbon bond. Whenever we have the substitution, at the substituted carbon-carbon, we need to cleave that bond, thereby we can get the molecular ion. So this is about what? The molecules containing sigma electrons. If the molecule containing both sigma electrons and pi electrons, already we know that pi electrons can easily removed than comparing with the sigma electrons. That's why initially we need to remove the electrons from the pi bond. This one, it is the pi bond containing molecule. From the pi bond we have removed an electron. So this is the cyclic olefin. In the cyclic olefin we are having a pi bond, thereby we are creating one molecular ion. In case of the benzene, it is also a pi bond containing molecule. All pi bonds are available, so we can remove any one of the electron from the any one of the pi bond, thereby we can create a molecular ion. Next, the molecules containing both sigma and n electrons. We already know that comparing with the sigma electrons, n electrons are loosely held by the nucleus. That's why we can easily remove the n electrons. Generally, we can observe n electrons in case of alkyl or aryl halides. So we can easily remove one electron, thereby it can produce as a molecular ion. In case of alcohols, in case of thiols, in case of amines, and in case of ethers. We are observing both n electrons and sigma electrons. We need to concentrate on only n electrons. The last type of molecules are what? The molecules containing sigma, pi and n. If the molecule is having these kind of electrons, what should we do? Initially we need to remove the n electrons. So where we can observe this kind of situation? In case of carbonyl compounds, aldehydes, ketones, see this one, sigma bond present, pi bond present, and n electrons are also present. We need to remove the n electrons. Okay. In case of these kind of compounds, sigma bond, pi bond, and n electrons. So initially we can remove the electron from the lone pair, thereby we can produce a molecular ion. So in this way we can generate a molecular ion in different functional groups of organic compounds. Okay. The second topic is what? Stability of molecular ion. In order to have the stability, we have a sequence commonly called as Bemann's molecular stability order. Bemann's molecular ion stability order. According to this order, the molecular ion which is produced by the aromatic compounds are going to be highly stabilized. Why? Because that one is going to have in conjugation with the remaining pi bonds. Already we know that the molecules where we can observe the delocalization, the stability increases. So depending upon the common stability rules, here we have the order of the molecular ions for the different organic functional groups. Till now we have discussed that how to generate molecular ion in different functional groups of organic compounds. Right? Now we need to see the recognition. How can we recognize whether the peak in the particular mass spectrum is corresponds to the molecular ion peak or not? How can we identify? How can we recognize? In generally what happens in 95% of the cases, the last peak in the mass spectrum will be the molecular ion peak. But it is not necessarily molecular ion, but in maximum cases we are observing that what? The last peak in the mass spectra is commonly called as molecular ion peak. Okay. How can we recognize? In order to recognize the molecular ion peak in the mass spectra, what should we do? Suppose assume that this is the peak. We want to say that it is a molecular ion peak. In order to say that particular peak is a molecular ion peak, what should I do? Identify immediately left peak. See this one? This peak corresponds to M by Z 92. So immediate next peak is what? 91. Subtract these two, 92 minus 91, that is equal to what? 1. It is giving the number 1. It is corresponds to what? Hydrogen in the periodic table or not? then you can say that this particular peak is molecular ion peak. It means that what? Simply, in order to identify the particular peak as a molecular ion peak, just immediately identify the left side peak and do the subtraction. If the subtraction value corresponds to any kind of the species, like the weight is corresponds to methyl group, ethyl group, OH group, NH2 group, SH group, then we can say that the identified peak will be the molecular ion peak. Suppose assume that the weight of this peak is 100. Okay, immediately left side one is 85. What is the difference? 100 minus 85 means what? It is 15 or not? The 15 value corresponds to methyl group or not? It means that what? The subtracted value is going to correspond to the particular substituent, methyl substituent. That's why this particular peak is commonly called as molecular ion peak. So in this way we can easily recognize the molecular ion peak in the mass spectra. Okay, the last component in this particular lecture is what? Utility of molecular ion. What is the use of the molecular ion? Already we know that molecular ion is formed from the molecule or not. Molecule is a even electron molecule, right? From the molecule what we are doing? We are removing a single electron or not? The removal of single electron producing your molecular ion. The mass instrument is recognizing what? This molecular ion or not? How can you get the molecular ion? Molecular weight by the charge of the electron. Electron charge is 1. That's why what happened? If you know the m by z value of molecular ion, that is going to be equal to the what? Molecular weight of the compound. So indirectly what we are observing, the molecular ion recognition gives the molecular weight of the compound. Okay? In case of multiply charged ions, what is the formula? Molecular weight of the compound equal to m by z value of molecular ion into charge value. In the simple ions what happens? Charge is only 1. In case of multiply charged ions, the charge will be increased or not? That's why what we are doing, charge into m by z value of molecular ion. See this one, in case of the pyridine, the m by z value is what? 79 by 2, that is equal to what? 39.5, that is the weight of the molecular ion. 39.5 into charge, that gives what? 79. So in this way we can utilize the information by using the molecular ion. So this is all about the origin, stability, recognition and utility of molecular ion.